I
No,
can't.
no, we can't.
Okay, so the problem is my end. Okay, let me just make sure I'm sharing. Okay. Yeah, go ahead. Can you see my screen now?
Yeah.
Okay. Welcome everyone. This is day 12 and session 2, and this is for the next generation technologies. We have this Ministry of Education Pandit Madan Mohan Malviya National Mission on Teachers Training, organized by Ramanujam College, OTF, and the uh, FROST, along with the Ministry of Education. And we have faculty members from the universities and government departments and research associates. And we welcome Professor Dr. Umakant Rapol, who is a leading an experimental atomic physics group at IISER Pune. The primary focus of his research group is in using ultrasound atoms and ions for studying quantum physics and developing quantum-enabled technologies. His research areas include atomic physics and precision spectroscopy, quantum optics, and quantum information processing, biosensors. He's a humble guy. He has led the team which is working towards making sure that we have development of photonics and equipments that will be able to use for the quantum computing in the analog domain, which are at the low temperature and all. So he is very devoted and very hard to get him. We are fortunate to have him today. And go ahead, floor is yours, Makant, and lead the faculty through what we need to do to understand the quantum computing. Thank you, sir. Go ahead, share your.
Thank you very much for the kind introduction.
Yeah, go ahead, share your screen. I can stop sharing.
Can you see my screen?
Yes, we can see your screen.
Okay, so good morning, everybody, and thank you very much for the kind introduction. I would like to give a small overview about how quantum computing is done, taking an example of ions in an ion trap, of the work that is currently going on, or that the work that went on in some groups abroad, especially at Innsbruck. And also I will give a short overview about the research that is going on in our group at IISER Pune. So we all know that quantum computing has picked up a lot these days, and there are reasons for why quantum computing is being sought after so much these days. And the reasons are quite obvious, because as classical computers started evolving, all the devices that go into classical computers, they started becoming smaller and smaller. Over time, the number of transistors that go into building these processor circuits, which are at the heart of classical computers, they started increasing. But then how far can this number of devices keep on going on increasing? Because at some point you're going to hit a limit. And as we all know that once you go on a scale of atomic or molecular scales, then classical physics laws kind of hit a roadblock, and all the physics that goes on needs to be explained with quantum mechanics. So that's where the emergence of quantum bits or qubits come into picture, or using quantum mechanical bits for doing classical quantum computing. So what's the difference between a classical and a quantum bit? So a classical bit is basically a logical 0 or logical one state, which is defined by certain voltage levels in your circuit, and you play with those voltage levels and then use memories like flip-flops, which are the basic building block of a memory, to store the information, to store your classical bit, the voltage level high or low in these flip-flops, and start building up memories and registers and arithmetic processors, and then build up larger, say, for example, a CPU, which goes into a computer, or many other smaller devices, microcontrollers, etc., which go into all these IoT devices and even your simple phones, for example. Now, what are quantum bits as opposed to this? Well, I mean, it's again, now we are talking about not a collection, not a macroscopic system like a transistor, which is actually processing your voltage levels, but we are talking about even minuscule scale systems like atoms or photons or electron spins or currents which are flowing in superconducting circuits, etc., which all behave laws of quantum mechanics. Now, here I have taken an example of a calcium ion qubit on top here. So forget about this S half, P half levels. But if you look at some other levels, which is this S half and D half, D5 half level, these are basically two levels of an atom. Now, the state in which the electron resides, like either on the lower state or the upper state, is your logical 0 or 1 state. But then there is more to it. It's not only the level where the electron stays, but quantum mechanics also dictates that not only these are levels where your state can reside in, but you can also get superpositions of these states. For example, the graph here shows the population. So if you do many measurements on, say, an atomic qubit or any other qubit, once you do a measurement, you get a definite answer. So if you do 1,000 measurements, if half the times if you find the system to be in the ground state and half the times in the excited state, it means that the population is half in your ground and excited state, and it's the state, that result is because of a superposition that exists between the ground and the excited state. Now, this similar system can be imagined with the polarization states of photons. So normally we know that, I mean, when light travels, a polarized light has certain polarization. Of course, not always do you have completely polarized light. You also have completely unpolarized light also. But if you look at photons, single photons, they have a definite polarization here. Either you can label them as being horizontal or vertical, depending on what frame of reference you have. You can generate a superposition of these horizontal and vertical polarizations and represent them appropriately. Same with an atomic qubit or a superconducting qubit. Now, why are these quantum mechanical bits or qubits superior? Because of the existence of the superpositions of the ground and excited state, or existence of the superposition of the two possible states of a quantum mechanical system. And not only that, but you can also have multiple qubits entangling themselves. So this resource of the quantum mechanical bits, the superpositions, the entanglement, these are an added resource that you get on top of what your classical bits offer. So that opens up enormous possibilities on doing computation. For example, there have been certain algorithms that have been shown that which work much faster on quantum mechanical system, like factorization algorithms that have been developed by Peter Shor and et al., that you can actually factorize very large numbers where the time that you take to factorize goes as a polynomial in the length of the number. Whereas if you take a classical computer and try to do a similar computation, what happens is that your time increases exponentially as the number of as the length of the number that you want to factorize increases. You can do cool things like quantum teleportation, which is nothing but transporting the quantum mechanical state to some other state, or transporting the quantum mechanical, copying the quantum mechanical state. I mean, it's not really copying, but it's called teleportation. You can do quantum simulations. Basically, what you do is that, for example, if you want to simulate a large molecule, or say if you take a protein and you want to know how it folds onto itself. I mean, this is a big problem. Protein folding is a big problem in pharma industry and also in biological sciences, biochemistry, etc., where it becomes extremely non-trivial to do simulations in a classical computer and find the exact solution. Or if you want to know, if you want to do some drug designing of pharmaceutical drugs, then it becomes more and more tedious as your size of the molecule keeps increasing. So actually, in order to simulate such systems, you don't use a classic. I mean, the future is that you are not going to use a classical system, but you use a quantum mechanical system itself to actually find the answer to another quantum mechanical system. So you find analogous quantum systems where to the desired problem. I mean, if you have a certain problem to be solved, you find an analogous system, and in most of the cases there are Hamiltonians which describe the actual system. You actually simulate those Hamiltonians on another quantum mechanical system and get the answer and then map it onto your original problem. So that is what is called as quantum simulation. You can do quantum cryptography, which becomes very, quantum cryptography is a tool where you actually encrypt information, and it becomes very difficult to actually, most of the time it becomes not only difficult, but also you get to know if the information is actually eavesdropped on the way. And one can use quantum logic, the superpositions, principles of superpositions and entanglement, to actually build very precise atomic clocks, which lose less than a second in 10 to the power 19 seconds or so, which is like more than the age of the universe, for example. Now, what are the metrics? I mean, these days you keep hearing about the number of qubits that have been increasing, and there are a couple of companies which are leading this way, like IBM, Google, etc., Honeywell. Every year you keep hearing about the number of qubits that have increased every year. Now, what does this mean? I mean, what is the metric for how good a quantum computer is? First of all, it depends upon how many qubits you have in your system. Like in a classical computer, you have whatever 32 or 64 bits that decides the length of the basic registers that are used for processing all the information. In this case, it's the number of qubits that you have. And how many gate operations can you do on these qubits before the qubit loses its coherence? What I mean by coherence, I'll come to that very soon. So then how many links you have in your, if I have a string of qubits, say 10 qubits, how is each of these qubit connected to the rest of the qubits? How many qubits is it connected? These are called the links. And then one very important aspect that comes into picture when you talk about quantum computers is that because of the stochastic nature, because of the quantum mechanical nature, probabilistic nature of computations on a quantum computer, these systems are prone to errors. Quantum mechanical systems are very fragile. So there can be decoherences, there can be other issues which can perturb these quantum mechanical systems like atoms or photons or ions, or superconducting qubits. There you get to come across quite a few errors when you are doing your manipulation of the state of the qubits. Now, these error rates are going down and down day by day because of the improvement in the way the qubits are manipulated, including the ways in which the gate operations are implemented on these qubits. Now, that has made people to think of some particular number to say that, okay, my quantum computer is this large. So that metric is called as a quantum volume. And the latest system using 10 qubits ion trap quantum computer, as far as I know, is by Honeywell, which has been released in very recently. This news has come. And then there are other companies like IonQ, which are developing ion trap based quantum computers. And then you have the superconducting qubit based quantum computer by IBM and Google and Rigetti, etc. Okay, So what are the various quantum mechanical systems that are platforms that are used for quantum computing? So there are broadly two types. One is quantum optic systems, which comprises of atoms in optical lattices, which are periodically arranged atoms in optical lattices, lattice which is formed by uh, interfering electromagnetic fields or laser lights, ions in an ion trap, strongly coupled atom and photon systems in cavities. So you have atom and you have an optical cavity where you confine electromagnetic radiation, and then you have the atomic states or the atomic dipole moment strongly interacting with the cavity's field. That is one of the system. And then there is this photon down conversion systems where you generate entangled photons naturally by uh, using nonlinear optical crystals, and you put in light of a certain wavelength, and then you get two photons of twice the wavelength. So there, the photons that are generated are entangled. So using these entangled photons, people are trying to do quantum information processing and also for quantum communications. The other broad class of systems are the solid state systems. So solid state systems are basically formed of this variety of platforms. One is this superconducting Josephson junctions, which are basically two superconducting strips which are separated by a thin tunnel junction formed of an oxide, and there you have this persistent supercurrents oscillating, and those are used for processing the quantum information. So the direction in which the current flows is the state of the either your 0 or 1 state. Then two-dimensional electron gas in 2D heterostructures, quantum dots. Then other platform that is gaining a lot of attention these days is using nitrogen vacancy centers in diamond crystals. So these nitrogen vacancy centers are basically defects, color centers, defects, which act like single atom, and they have well-defined ground and excited states, which are used for quantum information processing. Okay, now once you have such systems, I mean, how do you decide which system to go for quantum information processing? Okay, so there are a few criteria. So, and these criteria are well summarized by DiVincenzo, and they are these. First, you should be able to initialize the state of these qubits. You should be, like in a classical bit, you should be able to start your system either in logical 0 level or logical 1 state. Then you need to have long coherence times. What I mean by long coherence times is that so quantum mechanical systems, like the example that I took about the atom, two states of an atom, the ground and the excited state. The excited state is, once you excite the electron to the excited state, it's not going to remain forever there. It's going to decay naturally after a certain time. Now, that lifetime decides one of the coherence times. And then once you entangle this atom with, say, another atomic state, which is like entangling two qubits, then also there is a decoherence that sets in. All this is because of the interaction with the environment. And these coherence times have to be very long, because all the gate operations that you would be doing on these qubits has to be such that the state, for example, the excited state lifetime should be much, much larger than the total amount you spend in executing the gates. Then you need to have a universal set of quantum gates. Like in classical computers, classical digital electronics, you have NAND gates, which are the universal gates. Using NAND gates, you can build any type of gates or any type of flip-flops, and then thereby registers and memories. There, in quantum mechanical systems or for quantum computers, you need to have a universal set of gates. Then you need to be able to read the state of the qubit. So if my atom is in the excited state or the polarization state is in one of the polarization state, then you need to be able to read it out and say that, okay, my qubit is in ground state or an excited state. Then the most important aspect, which currently everybody is struggling with around the world, is scalability. Scalability is nothing but how many qubits can you put in one physical location. So like in a classical computer, like I said, you have 32 bits or 64 bits. In case of quantum computer, you can't just increase the number of qubits indefinitely, because once you start increasing the number of qubits, then what happens is that the overall quantum mechanical state of the collective state of the qubits, say if you create an entanglement of these qubits, then the fragility increases non-linearly as you increase the number of qubits in a physical system. So scalability is a big issue. So that is something which everybody is working on, like the Honeywell ion trap computer, which I said right now they are at 10. Now, if one can easily increase the number of qubits, but then the other parameters like the coherence times, all that gets damaged drastically. Okay, there is an additional criteria. Now, talking about scalability and all that, there is an additional thing like so the earlier criteria, these 5 criteria which I mentioned, they are for single node quantum information processing. Now, if you want to scale the system to physically separated quantum mechanical system, then you get to encounter these 2 additional criteria: interconversion of stationary and transmitted qubit, and there has to be a channel where there is no loss of the quantum information. So that is typically photons which are transferred from one physical location to the other. So I'll just take an example of a calcium ion system, which are these experiments done at the Institute for Experimental Physics at the University of Innsbruck, where I had worked in the past, long ago. I'll just take examples, a few examples of how one manipulates this quantum mechanical bits. This is just an example. There could be other systems also. Now, the system under discussion is what is called as a calcium plus ion. So this is a singly charged calcium ion, calcium 40 isotope. Of course, there are other isotopes also of calcium 43, etc. 43 which can be used. And then there are other systems, ion trap systems, which people are working across the globe, and those are ytterbium ions. There are these beryllium ions on which people have been working on to develop this quantum computers using ionic systems or ionized atomic species. So I'll just take this example. So this is their experimental setup. So as you can see, now things are getting more and more compact. There's a huge mess of laser systems, electronics, control systems, etc. And deep inside here in the vacuum system sits an ion trap, which is formed by 4 electrodes, and you apply an AC electric field oscillating at several tens of megahertz. And then in between here, there will be a string of ions which will be trapped. Like here, there are 3 ions, the fluorescence from these ions, which are separated by a few micrometers. You can see it on the CCD camera, and then you can individually manipulate the internal state of this. Now, what's there inside this each ion, as I showed before? So there is a qubit transition. So there is a ground state and an excited state. At the ground state is S half. This is the spectroscopic notation of the electronic state of the atom, and then this excited state by D half. It's a quadrupole transition, and the lifetime of this excited state is about 1 second, a little over 1 second. Now, this additional transition is used to do other things like laser cooling these ions and getting them in the motional ground state. Now, these are some more details. So the 393 nanometer and 397 nanometer are the transitions which are used for laser cooling these ions. And then this 866 and 854 nanometer lasers are used to clear these D levels when there is a laser cooling. When there is a transition here which is driven, there is some probability of this excited state getting decayed into these. So these are cleared with 854 and 866 nanometers. So different ionic systems and different atomic systems have different energy level schemes. So one has to use lasers appropriately. Now, after the laser cooling is done, then the state can be initialized in this ground state, and then this particular transition from the S half to D5 half. This D5 half is the logical 1 state of the qubits state. These are your 2 states of the qubit, and then you can generate superpositions of these 2, etc. Now, how does one address in their system? The way they address is, you say, for example, this is a real picture. of two fluorescence from two ions. So you can see that one of them, these ions keep blinking depending upon whether this particular transition is driven or not. So from S half to D half, and then you can actually, once it is excited, then there is no fluorescence from this 397 nanometer laser because the electron is gone here. But if the electron is in the ground state, then you see fluorescence here. So this is the fluorescence of the ion at 397 nanometer laser. Now, what happens when you take such an atom and put it in a trap? Now, the trap that we are talking about is an electrodynamic trap, which is this harmonic oscillator potential in which the ion is located. Now, once you put a quantum mechanical particle in such a trap in any potential well, which is shown here, it's a harmonic potential well, then the particle can occupy one of these quantized energy levels, which have a certain separation. Here it's given by this nu here. And in case of this harmonic trap, a three-dimensional electrodynamic trap, there are two frequencies. One is along the axial direction and one is along the radial direction. So these radial direction frequencies are higher than the axial direction. And you can actually excite different modes. I mean, you can excite the atom from one of these to any of these different levels. So if it's in the ground state, you can excite it to higher levels. When it's in the higher levels, you can either excite it to upper level or lower level. Now, this on the left side, you have the internal state of an atom, S and D. Now, this internal state gets modulated by the energy levels of the traps. So the combined system energy levels are shown here. So you have, this is when the atom is in the lowest ground state. So the 0 is the motional state. Motional state means these energy levels of the harmonic oscillator potential. Now, if you excite a blue sideband, which means, so this you can imagine as amplitude modulation of the light that is emitted from this light, from this atom, it will get blue and red sidebands depending upon where it is. So if it's in the ground state, it has only blue sideband. So if you excite a blue sideband, you will excite one motional mode and the internal state goes to the excited state and so on. So you get a ladder of these energy levels. Now the coherent manipulation of this state is done by either exciting directly, which is the carrier, or the blue sideband, or the red sideband. So if you excite a red sideband, it will, if you are in 2, you come to S here. I mean, if you are in 2 and if you excite with a red sideband, you come here and so on. And the blue sideband will take you from this to this. Now, so coherent state manipulation. First is you need to be able to create a superposition of this ground and excited states, which is the most important resource in quantum computation. That is, so if I take an atom here, if it's in the motional ground state, you excite with a carrier on this transition, and then there will be a coherent drive from 0 to 1. I mean, the ground state to the excited state, the 0 and 1 are the motional states. So if you do a coherent drive, the population, and you measure the population, repeat this experiment, say 100 times, and then you can measure the population as a function of the driving time of this particular transition. Now, as the time increases, you see the population oscillating from ground to excited state and back to ground state and excited state and so on. Now, this can be represented, this particular population swapping from ground to excited state can be represented on a block sphere, which is basically the poles of the sphere are your either 0 or 1 state of the atom. Now, this rotation of this, I mean, the state vector on the block sphere, that can be rotated using unitary operators. I mean, this rotation can be represented by unitary operators on the block sphere. Now, if you do a carrier excitation, you only excite the internal state and not the motional state, as I said. But if you do a blue sideband, which means you excite the internal state from S to D, plus you excite one motional mode. So on the carrier, you have these Rabi oscillations, the population flopping from 0 to 1 and back is called Rabi oscillation. Now, this is on the carrier. The frequency of that is much faster. I mean, the flopping can be done in a much shorter time. Whereas if you go to blue sideband, then it takes a much longer time to excite the blue sideband, because the coupling efficiency of the light, or the strength that is needed to drive this transition, is much more than the strength that is needed for driving the carrier transition. So that is decided by this factor called as the lambda-Dicke parameter. It's basically the extent of the wave function of the atom inside the trap, how it overlaps with the motional modes. Now, using these basic manipulations of driving the atomic state either on the carrier or on the sideband, one people have implemented many different basic proof of principles of this quantum mechanical manipulation, state manipulation. Now people have created two-particle Bell state, created a controlled NOT gate, entangled 3 ions and many ions together. And these kind of things have been implemented on other platforms also, not only ions, but many other platforms like the superconducting qubits, etc. Now, I'll just give you an example of how these two-particle Bell states. So two-particle Bell states are nothing but, say, these are represent, so there are 4 possible states here. S and D represent 1, 0, and 1, which is the ground and excited state. So if you have 2 ions in the ground state, and if you create a state which is superposition of the ground states of both ions and the ground states of the excited states of both ions with a plus sign, this is one state, and then you have 4 possible states. So SD plus DS, SS minus DD, SD minus DS. These are also called as EPR pairs. These pairs here are called as EPR pairs. Now, how does one create a Bell state with 2 ions? So you have these 2 ions in a trap, and you initialize the state, which is an important criteria given by DiVincenzo for using this quantum mechanical systems for quantum computation. So these are the 2 ions here. The states are initially SS. So this is ion 1. These are the 2 internal states. These are again 2 internal states, but with an extra motional state. Now what you do is that you come with a blue pi pulse. So you excite the pi by 2 pulse. You excite the ground state to excited state in such a manner that the population is half-half in the ground as well as the excited state, but also a motional state which is excited. Now you create this. So SS0 plus DS1. So the first one is this shown in red. Then what you do is that you come with a carrier pi pulse, which basically transfers the population of this on the ion 2. You come with a pi pulse. You take the population, transfer the population from ground to excited state on ion 2. And this one, since half of the population is already in the excited state, it just remains there. So what you create is you create this particular state, SD0, which is motional state, plus DD1. So this is a superposition of the internal states and the external motional state. Now what you have to do is you have to get rid of this phonon mode, which is the motional state, which is in 1. So what you do is that you come with a blue pi pulse. So this state doesn't go anywhere because there is no mode. This is already in the motional ground state. So there is no other mode below the motional ground state. However, the excited state here with the motional mode 1, it actually comes back to this lower ground state, and then you create SD plus DS state. Now, by manipulating the phase of these pi pulses and carrier pulses, you can actually change the sign of this superposition here. So you can create different states, SD plus DS, SD minus DS, by a sequence of these pulses. So this is like, so this is your initial state. You come with a blue carrier with blue carrier pi by 2 pulse with a phase of minus pi by 2. Then you apply a carrier pulse, then you apply a blue pulse. So it goes first pulse, second pulse, and third pulse, so on. So depending on the phases, this phase of the final pulse here, you can actually change the sign. Then you can also create such superpositions also, SS plus DD or SS minus DD, depending upon the pulse sequences. Now one can actually look at the decoherence of this entangled state by looking at what is called as a parity. Parity is this sign here. So this one oscillates with time. You create such a state and look for the oscillation signal, which is the parity signal. And then you see that it decays over time. So in this case, the data is up to say 0.5, half a second. And then you measure the decoherence time. That's about half a second or so, the decoherence time. You can also create a robust entanglement, because here the decoherence is mainly because of the excited state being used as your logical one state. What you do is that you transfer that population to one of the ground magnetic sublevel states. There, the decoherence is much longer. So one can get several tens of seconds of decoherence time by choosing what is called as a decoherence-free subspace. Now, the other important gate, so okay, so that was a demonstration of a two-particle entanglement. Now, we have seen that you can manipulate the single qubit gates, which means single qubit rotations are one of the two universal gate. The second universal gate is what is called as a controlled NOT gate. So what is a controlled NOT gate? So if you have, say, two ion system, for example, 0, 0. Now, depending on the state of the control bit, so I call the first one as control bit, second one as say target bit. Now, depending on the state of the first control bit, the state of the target bit changes. Now, in this case, the state of the control bit is 0 in the first two cases. And then what happens is that when you apply a controlled NOT gate on this particular state, the second qubit state doesn't change. However, if the control qubit state is in 1 and the state of the target qubit changes. So if it is 0, it becomes 1. If it is 1, it becomes 0. Now, these gates are one of the fundamental building block gates for any quantum computer with any number of qubits. Now, there are other proposals also, and there are other demonstrations of different types of gates. So this one is Dirac-Zoller gate, and then there are other gates which I have mentioned here, and then there are many more implementations that are coming up. Now, the way the controlled NOT gate operation is done, one of the implementations is here. So you have the two ions, or ion 1 and ion 2. So this is ion 1, this is a motional state 0. And what you do is that you swap the internal state with the motional mode. So using the first ion, you swap the internal state to the motional mode, and you apply you do an operation on the second gate depending on the state of the motional mode, and then the target qubit state changes, and then you swap back the motional mode back into its original motional mode. So this is how the Dirac-Zoller 2-qubit NOT gate works. So ion 1, ion 2, you do a swap on ion 1 with the motional mode with the blue pi pulse here, and then what you do is that you do this particular operation here. Basically, you do a 2 pi rotation on the Bloch sphere and get a minus sign on this particular state, and then you swap back the motional mode back onto 0. Now, this is a basic C0 gate demonstration. So after the final blue pi pulse, this state just goes back. So one of the important thing is this composite phase gate, which is this particular sequence here. And that is operated by taking the population from the from the ground state, internal ground state, to an internal excited state plus a motional mode, and then you bring it back here. So when you take the population, circulate the population on the Bloch sphere using a motional mode, you get a phase factor of -1, and that's shown with this particular operator in the matrix form. Now, the composite phase gate is basically composed of these 4 pulse sequences. So first, initially, your state is here on the Bloch sphere. You take it down, then you turn it around by changing the phase of the pulse, this particular, the second pulse. And then from there, you be on this, going on this red track, using the third pulse, you take it to the other pole of the Bloch sphere, and then bring it back with the last pulse. So when you look at this trajectory on the block sphere, when you complete the circuit, you gain a phase of 2 pi. So that is decided by how much of the surface of the block sphere is covered. So solid angle is covered in doing a complete circulation over the block sphere. So that gives you a phase of 2 pi, and it basically you go from S0 to D1 and D1 and then back. So that gives you a phase factor. Now one can create such states also, 3-qubit entangled states. So this is a GSZ state, Rinberger-Hor-Zeilinger state, where you have a superposition of all 3 qubits in the ground state with all 3 qubits in the excited state. So these are very fragile states. And then you have the W states, which are basically either one of the qubits is in the excited state, and then you have a superposition of those. And these are quite robust. And then the way you characterize these all these states is by building a density matrix. So this is a density matrix. So as you can see, these bars here on the 4 corners are this DDD, SSS, DDD, and then, I mean, it's basically you have to read it by looking at the overlap of this SSS and DDD state, and in this case it is SSS and SSS states overlap. So that is the density matrix here. It's a mode of density matrix. This is the real part and the imaginary part. Now these are very fragile. And then the W states are essentially this. So these states, for example, GHZ state before and after measurement, you do a measurement on one particle, the entire state collapses. Whereas in the W state, you do a measurement and then on one particle, the state retains its coherence on the other state. So these are more robust states. Then you can do even more number of ions entangled state, and this is a 8-qubit entangled state, W state of 8 qubits. So this is a complete density matrix of 8 qubits entangled state. Now, so this is about single node quantum computing. So that was an example of just ions. So it could be single atoms also, it could be photons, it could be some superconducting circuits. Now, if you want to do if you want to scale the number of qubits, if you keep increasing the number of qubits in one node indefinitely, what happens is that, as I mentioned in the beginning, there are going to be a lot of interfering effects from the environment, which will kill the coherence of the combined state. Now, in order to overcome that problem, one of the things is that you don't put all the qubits in just a single physical location. You put a few qubits in one single location, and then few more qubits in another physical location. And then what you do is that you transfer quantum information from one location to the other, so that you multiply the number of qubits in some fashion. And as I mentioned in the earlier, so if we look at this second set of DiVincenzo criteria for distributed quantum information processing, you need to have an interconversion ability of qubits. I mean, between transmitted qubits and the physically located qubits. And then there has to be a channel where there is no loss of quantum information. Now, with single node quantum computing, many things have been realized, including implementation of certain algorithms like factorization, etc. Now, if we look at the classical case of distributed information processing, so you have different clusters located physically in different locations, and then they are all connected with some fiber link where your classical bits are transmitted from one node to the other. And then if these are physically very far away, then you have this classical repeaters where you just amplify the signals that are amplify this logical 0 and 1 that are going over an optical fiber. Now, in distributed quantum information processing, you have different nodes which are quantum mechanical systems, and then you want to transmit information which is basically superpositions and entangled states from one location to the other. Now, the thing is, I mean, you cannot have classical repeaters which are similar to classical repeaters, because you cannot copy quantum information and then amplify it and transport it, because once you make a measurement on a quantum state, then you lose the information of the quantum mechanical state. Now, these are various nodes for a quantum in a distributed quantum information processing platform. So you have vapor cells, you have ion trap based cavity QED systems, neutral atom based cavity QED systems, nanophotonics coupled to waveguides, etc. Now, the as I said, the problem is, I mean, you cannot transport this information over very long distances, because there is attenuation of the signals and you keep losing fidelity. Now, in classical repeater, it's simple. I mean, you have amplifiers, photodetectors, and lasers. You have your input bits, you put it on a photodiode, put an amplifier, and again have a laser diode or something, which again, basically attenuated signal, you again amplify in a sense and transport it over the fiber. So these are your classical repeaters. You cannot have same thing as I mentioned, because of a no cloning theorem in quantum mechanics. You cannot just have a quantum mechanical state which is transported with some by copying it. So that's not possible in quantum mechanics. So what is done typically is that, so if you have node 1 and node 2, and the repeater, basically what it does is that you entangle the state of the quantum mechanical state information that's coming from node 1 in a repeater, and then you entangle the other state with this in this junction here. So what happens is that with node 1 and node 2, you can get an entangled state. So this is how the principles of quantum repeaters kind of work. Now, repeaters, the essential things for quantum repeaters are you need medium to store quantum information. So these are typically, as I said, atoms or ions or vapor cells. And you need to have interfacing systems for light. Typically, light is what you use as a channel to transport quantum information from these nodes to the repeaters. So you need to have some interfacing systems for interfacing the atoms, or the quantum memory with photons. And then you need to have basic protocols for gate operations. Now, the coupling of stationary and flying qubits, so which is essentially this interfacing of light matter systems, is basically, so you have an atom. I'm just taking an example of atom. It could be any other quantum mechanical system. So you have a quantum system 1. Now you have, say, if you have an electron in the excited state and it decays to the ground state, it's coherently driven to the ground state. There is an emission of photon, which you collect efficiently and then transport it over a link. And then this photon is actually goes and excites the atom from the ground state to the excited state in a different node. So this is the basic thing. But then what happens is that you know that the photons that are emitted by atoms, for example, they are not completely directed. They can be emitted in any direction. So you have to make it emit in a particular direction, and that is done using various approaches. So in quantum networking, there are two fundamental approaches. One is deterministic and one is probabilistic. I'll just give an example of deterministic, how deterministic networking is done. Probabilistic, I will not get into it. And I'm running short of time. I think I'll wrap this up soon. So for in deterministic quantum computing, you have these individual material qubits, atoms or ions, which are used as your quantum memories. And then there has to be a coherent transfer of quantum information to these flying qubits, which are photons. And you have to have highly efficient emission of photons into the direct desired modes, which you want to transport over an optical fiber link, for example. And you need to have larger fidelity, because this particular system has larger fidelity, but it is prone to noise. Whereas there are, in the probabilistic means, you use ensembles of atoms as quantum memories, and then you rely on post-selection based on post-selection for taking out entangled photons and for transferring quantum information. Now here, this is less prone to noise, but then the success probability is low, but then the number of trials that you get to do is much, much larger. So probabilistic also has certain advantages over deterministic. In deterministic transport, the coupling schemes that are used for photons and atoms They are typically based upon cavity QED systems, and we are working on coupling of atomic dipoles to plasmon excitation in some kind of nanostructures, where you couple the atomic dipole moment to the plasmon excitation and get the photon out in a deterministic manner. Then you use platforms such as oscillating charges, which are coupled to superconducting links. Then you have quantum dots, which are coupled to micro resonators, which I had shown earlier. So these are some of the schemes that are used for coupling. So this is an example of a single atom in a photon. So you have an atom with two internal levels, one ground and one excited state. And these are two mirrors. This is a cartoon of an optical cavity which can support only a particular optical mode. Now, this mode volume is very small. So, and when you put an atomic dipole in such a configuration, what happens is that the atomic dipole becomes very strongly coupled with the electromagnetic fields mode here within the cavity. And there are certain parameters that characterize how good your cavity is, how good the atomic dipole is coupled to the cavity. And in some regime where so this G, which is the coupling of this atomic dipole moment with the electric field inside the cavity, that has to be much larger than the spontaneous decay rate, because once you excite the atom, it's going to decay spontaneously. And there is also loss of photons from the cavity. So these two loss rates, kappa and gamma, should be much smaller than this coupling rate. Then you are in a strong coupling regime. When you go to that regime, you have uh, very interesting things that emerge out. One of the things is that when the atom de-excites to the ground state, because of the strong coupling, the photon is emitted preferentially only into the cavity mode. And thereby you get a photon which can be coupled out of the cavity, which is basically a directed emission into the cavity mode, which is an essential requirement for transferring the internal quantum information of the atom onto a photon. Now, using this, people have done such experiments. So you have, say, two nodes. This is an atom in one of the, so this is a cavity in which you have the atom, and then you have certain lasers to manipulate internal states. So there is a pump laser and there is a probe laser. So these are the two ground states, and this is the excited state. So this is cesium atom, I think. And what you do is that you have a coupling light which excites this atom into the from ground state to the excited state, and when it decays onto the through a probe onto this other ground state, it emits a photon into the cavity mode, and that cavity mode goes and actually enables the atom to decay from the particular from this particular state to this state, which is B to A. Now, these two are physically separate locations. Okay. Now, using that, one can do various things, like you can get what are called as photons. You can generate photons on demand with cavities, which are essential for some of the quantum information transfer schemes. And you can think of building such elementary quantum networks. So you have one node where you have atom inside a cavity. These are the two internal levels. Both are in the ground state, but different hyperfine levels. So it could one of them is 0 and 1, other is 1. So these are your logical states of your of your qubit. And then you can use this coupling laser to excite this atom and transfer it coherently into the other ground state. And then when the photon is emitted into the cavity mode, this red color photon, you take it over an optical fiber. And then on the other atom, what you do is that you take it from this lower ground state to the other upper of the lower ground state. So you basically do a coherent state manipulation of a distant atom based upon the state of the atom which is located at, say, this node A. So these are distant atoms which are coupled with each other via photon, and this is your quantum information transfer in a quantum network. So you can do storage and readout. So in this case, this is the ground state. This is the F equal to 2. These are the excited states. So the way you store it is that you Once you initialize the state here, then you come with two laser lights of certain polarization. This depends upon the, the excited states magnetic sublevels. And then you excite it coherently to this and this state, and then from there it decays. It is driven coherently down to the other ground state. And then if once the atom goes into these states, you can coherently drive it into the other one of the two ground states. So this is a block sphere that is representing the state of this internal states of this atom. So this is storage. So you excite with this take here. So you store that information. Basically, you go into the states and then remain there forever, and that's storage. And then to read out, you come with this pi. The pi and sigmas are the polarization states. Pi is linearly polarized. Sigmas are circularly polarized, either left or right. Then this is a scheme for what I told you earlier. So this is at node A, this is at node B, and you create by using this pi light, which is the pump, you create a superposition of these two ground states, for example. Now, these photons are entangled, and that you take it onto a fiber link, take it to the other node, and there what you do is that you had initialized this into F equal to 1, MF equal to 0 ground state. With these two photons which are coming from there, you again coherently excite that state and transfer that population into these F equal to 2 different MF states, -1 and +1 state, and you create a superposition. So you have transferred this superposition from one node to the other. So this is an elementary quantum network. So this is how you use it. So this distance between the nodes can be anything, depending upon how much losses are there in the optical fiber of these photons. So that decides how far they can be. Now you can have many of these nodes together to actually do a network, build a quantum network. Now in our group, we have couple of things going on. So we are working on distributed quantum information processing, where we are trapping and coupling single atoms near plasmonic nanostructures for essentially replacing the cavity QED system with the atom plasmon system. Then we have experiments where we are controlling engineering decoherence in atomic system. We are also working building atom interferometers using ultra cold atoms. And we have other experiments that are going on, where we are using engineering the short and long range interactions between atoms. Now, these are my current students, Pranab, Kushal, Korak, Shivsagar, and Jay, and my former students. Now, this is how my lab looks like. So here we are actually doing quantum simulation experiments and atom interferometry experiments using ultra cold atoms in a Bose-Einstein condensate. So these are the pictures of a Bose-Einstein condensate. This is a thermal vapor of atoms, which is ultra cold atoms at microkelvins temperature. And then this is a Bose-Einstein condensate at about 100 nanokelvin. So these atoms are cooled in a crossed optical dipole trap, where you load this crossed optical dipole trap with these ultra cold atoms, and we generate a coherent state of matter called the Bose-Einstein condensate. So these are the images of thermal image, a thermal cloud of atoms, and then this is a BEC, Bose-Einstein condensate. Now, on the distributed quantum information processing side, what we are doing is we are using confinement of light near metallic nanostructures, which are disks-like nanostructures, where we create optical trapping field. Now, this particular thing here is this inverted hat is a potential to trap atoms. So we are going to trap individual single atoms near this plasmonic nanostructure. So that's the plan. And these are the images of these concentrated optical light fields. So in the dark regions, we would like to trap atoms. These experiments are ongoing now. And we are going to trap atoms, neutral atoms, very close to these nanostructures which are shown here. And then we are going to build an elementary quantum network between these atoms. The other experiment that I told about was this engineering decoherence. So we use ultra cold atoms. We used ultra cold atoms in a periodic optical lattice potential, and showed that we can actually go from modify the decoherence of motional states from an expected exponential to a power law, which is important feature because most of the decoherence is exponential in nature, whereas a power law is a much longer lifetime decay. So this is a very fundamental observation which we are going to extend to other quantum mechanical systems. On the matter wave optics side, where we are building atom interferometers, so this is an atom laser. On the rightmost panel, you have this stream of atoms which are coherent, coming out, extracted out of a Bose-Einstein condensate, and we modify the trapping potential in such a manner that we actually load atoms into this and then cool them below the Bose-Einstein condensate temperature and extract them out. So these are some of the experiments. So we have built atom interferometers using Bose-Einstein condensate. We are improving on that. Yeah. Thank you.
So, fantastic presentation, Dr. Umakant. We are really impressed with the depth and knowledge you have. I think we can extend by 15 minutes the question and answer because we do not have one program we cancelled. So we would like to really ask questions. So would you mind staying 15 minutes with us, sir?
Yeah, sure.
Okay. So let's begin with the first question, simple one. The complexity of the science here and the technology here, it involves multidisciplinary understanding for any new faculty to get in. You're talking of optics, you're talking of electronics. So what technologies one need to know to be able to even grasp this? Okay,
so quite a few actually. One is obviously laser physics, atomic physics, ultra high vacuum techniques, RF electronics, data acquisition and control, to name a few, and mechanical engineering, of course. So quite a few things are involved in order to set up these kind of experiments.
Okay, that gives at least some idea that you need a lot of subjects to understand. The second to follow up is that, are we talking of photon traveling instead of packet traveling in this under fiber optics? And if that is the case, does it have to be in two different locations? Can it not be on a semiconductor chip where you can put them together at a distance of 10 nanometers and 20 nanometers and create multi-node on a chip types using semiconductor?
Yeah, also semiconductor is also the kind of platform I have been we are working on, using nanophotonic structures on a chip. So instead of getting them very close, if you separate them out by several micrometers also, that's also fine. I mean, that also can be used for doing networking of qubits on the same physical location. That is also possible.
So is it that there is a geometrical limitation of qubits on a node? You said that in a node you can have only certain number of qubits. Are you talking of a node being a chip or node being just one gate?
I'm talking about a node being a system of qubits which are directly coupled with each other. Like for example, in case of ions, the coupling is due to Coulomb repulsion between the ions. They are ions, so there is a Coulomb repulsion. So the entire chain of ions acts like a large molecule. And like molecules, they have these excitations, motional excitations, leading to side bands and all that, like the Raman lines and the Rayleigh lines and the Raman lines in a molecule.
So when you talk about the side bands, you spoke about the green side band, the red side band.
Red and blue, yeah.
Red and blue sideband. Are they very similar to the ones we talk about when we do antenna radio? Like you have a sideband. Does it imply that we can use QPSK and those kinds of modulation on top of this? Like pulse modulation, which is the common.
So the thing is, I mean, in this particular case, the sidebands are coming about because of the modulation by the motional states. So you have the carrier, which is your internal, the frequency is decided by the internal state of the atom. And then you have the sidebands are basically equally spaced, coming because of the motional mode of the particle oscillating in the trap. So anyway, it's a quantum mechanical motion. It's not
It's
simple
different.
motion.
It is not the same thing as antenna engineering we talk. It is more to do with the optical and photon, and then there is a different. So example, in optical, what we do, we use the what you call road amps for amplification. Road amps. It's amplifiers basically, power amplifiers. You put on the and then amplify the whatever Snell's law. You get the whatever the for the travel of the light. You try to trap and then you amplify and those kinds of things. But when you say quantum state, you move from one to another entangled state. Then in that case, how does it differ? And is there a mechanical, like electrical conversion? So normally what we do take a optical, convert to electrical to optical, and amplify in between. Does that apply here? It's
no,
something
it doesn't apply in case of a quantum information case, because once you do a measurement on the state, you collapse the information of that state onto one of the basis sets, and then you lose the superposition information, entanglement information. So instead, what you do is that you entangle the other states in the other quantum state with this initial state, and then you do the swapping of entanglement. You don't directly copy.
Okay, so it is a transfer of entanglement from one to the another. Fantastic. So I think at this time I'll ask my last question before I let it go to Vipin. My understanding, of course, I'm an electrical engineer, so I may have my own understanding of it in different way. But there is a three-layer approach here. So you have got one at the analog level, which you are doing in your analog portion of it, all the lasers and all that, where you have the photon manipulation or maybe a spin SPDF atom manipulation, whatever those kinds of, which are capable of doing, which is at the analog level.
Or now, classical, yeah.
Yeah. And on top of it, you've got the digital hybrid or mixed signal interface we need for the semiconductor. And on top, you need the logical. So is this three-layer, we can, in simple terms, we can think of it as a three-layer implementation for a computational device or a computation?
Okay, so let me take back one step. So you have a quantum layer. The quantum layer is basically your core, which is comprising of qubits of any platform, atoms, ions, or photons, or superconducting qubits. Now the state is manipulated either by electrical signals, which are basically radio frequency or microwave signals, or with laser pulses. Now that is a hardware that sits on the quantum core. Now this hardware needs to be controlled with classical electronics through mixed signal, whatever, mixed signal architecture, digital pulses and analog waveforms to control intensities and to turn on and turn off the pulses, or to control the frequencies of the microwave or radio frequency. So that is one layer. Now, on top of that, what you have is you have a layer which will, between that and the user, there can be a multiple layers. First, the user has a problem that he needs to convert it into some quantum circuit. Then what you do is that you need to control that you need to transfer or convert that quantum circuit into a sequence of pulses or manipulation steps that you have to do on your qubits, which depending on whatever platform, these manipulation steps are different. Now that you transfer it onto all your hardware to generate these pulse sequences. So these are the different steps. Now there can be, for example, to convert your real life problem into a quantum circuit, there can be a lot of algorithms and whatever software and all that can go into that. And then once you convert it into that quantum circuit, then converting that quantum circuit into something that your quantum core can understand, then there are these many different layers.
Are we on a particular platform which you think you will be able to develop and deliver to India? Is that what you're?
So I'm currently working on setting up a quantum simulator with the neutral atoms. Parallelly, in a few, we will be setting up an ion trap quantum computer sometime soon, which can be scaled to some number of qubits. Right now, Honeywell, I think, has the best ion trap, computer with a large quantum volume. So we have capabilities, but it's only about starting to implement and get.
Thanks, Dr. Umakanta. And could you also tell us more about like a little bit about national mission on quantum technologies and applications, and where you see India as in the game of quantum computing? You know, nowadays we heard the news from Google that they are doing some stuff. China now. So, what do you think like such initiatives can help India, and where we are right now and what we can do in quantum computing stages?
I think this is a great step for us right now. So it is a big booster for enhancing all the knowledge base in quantum technologies that exists in the country. So it's going to bring all of them together and start working on building state-of-the-art technologies. I think the knowledge exists in the country now. With the NMQTA, there will be a big boost to actually bring all these activities together and towards a very targeted development of be it quantum computers or quantum sensors or other quantum metrology systems, for example. So it's going to be a very big boost. I think we are quite excited about this.
Yeah, I agree, and thanks, Dr. Umakant, for leading these efforts to get India into a lead position in quantum computing as well.
Thank you.
So on behalf of the organizing team, OTF, F. Frost and Teaching Learning Center, Ramanujan College, University of Delhi, we extend our heartfelt thanks to you, Dr. Umakant, for taking out time
giving
and
me
interacting
opportunity
with
to
us.
speak here. Yeah.
Thank you, sir, so much. Thank you.
Thank you very much.